Planets covered with oceans, and not a continent in sight. Worlds of lava ruled by infernal temperatures. Horizons where the suns go down 2 by 2. We are now discovering that the universe has extraordinary worlds, exoplanets. Planets that revolve around other stars than our Sun. Since the discovery of the first exoplanet in 1995, over 2,000 new worlds have been detected. Among them, there are some that look like Earth and may contain a life form. To understand what is happening on the surface of these exoplanets, to find out if these worlds can be inhabited, astronomers use their most powerful telescopes to scrutinize the sky. In the United States and Europe, in Chile and outer space. The discovery of these new worlds is an extraordinary scientific adventure, which started over 20 years ago. A quest that seemed impossible, but has disrupted our perception of the universe today. This is the adventure of obstinate researchers who went out to seek these new worlds. Michel Mayor is one of the pioneers of this adventure. He is a Swiss astronomer who, in 1995, discovered the first exoplanet by observing the stars.
Watching the sky is always a complex feeling. The first level is admiration because it is beautiful. Even years after, it's still amazing. With the naked eye, man can only see a few thousand stars. 2, 3, 4,000. It depends on how good your eyesight is. In fact, the Milky Way has hundreds of billions of stars.
Like Michel Mayor, for thousands of years, man has been observing the stars, wondering if they could be hiding other worlds like Earth.
All stars are suns and are equivalent to our own sun. But our sun shines more just because it is closer. Imagine that when you look at the sky, you see all these suns, and then you ask yourself the question, what if there are other planets that revolve around all these stars, just like ours do around the sun? That's a very ancient question, and we are only able to prove it today.
For a long time, these planets have remained a mystery. Around the stars in the skies, there is complete darkness. At first glance, there is not a trace of an exoplanet. So how do we observe them?
Let's just imagine a star here, with a planet on its side that reflects just a little bit of light from the star. And let's try to see what could be visible if we move away a little bit from this small simulation. Here we are, just a few meters away, and we can no longer see it. We are completely blinded by the light of the candle, or rather the star, obviously in this case. The planet only reflects a small part of the light that it gets from the star, and that's what makes it so hard to observe extrasolar planets directly. From a certain distance, they are completely outshined by the luminosity of the star.
Hidden in the light of the stars, exoplanets are invisible from Earth and are inaccessible. Their quest then seemed completely insane 30 years ago. Why waste time looking for things that we cannot see? Yet, in the 80s, some obstinate researchers decided, no matter what the cost, to go out and seek these invisible worlds. Jeffrey Marcy, one of these exoplanet hunters. This American astrophysicist is obsessed with the search for extraterrestrial life. In the 1980s, he dreamt of finding exoplanets in order to discover another form of life.
Our wonderful Earth is such an amazing place, filled with life everywhere you look. Vegetables, animals, and of course, most especially, intelligent life. And it really gives us the opportunity to ask the question, could there be life elsewhere on worlds around the stars we see at night?
But in those days, no one ever observed an exoplanet. Was this an impossible quest? How do we find planets we cannot see? Jeffrey Marcy has a trick to detect these invisible worlds.
So the question is, how can we discover planets around other stars when the planets don't shine themselves? And we have a trick. The trick is we watch the star, and as the planet orbits the star, the planet pulls gravitationally on the star so that the star moves.
Not being able to see exoplanets, Jeffrey Marcy wants to detect them indirectly. His trick consists in observing stars to find signs of the presence of planets. No star moves by itself. However, if a planet revolves around it, then the star also starts to turn around and vibrate with the gravitational force of its invisible companion. When a dancing star is detected in the sky, this shows that it is accompanied by a planet. In San Francisco, Jeffrey Marcy is equipping a telescope with a spectrograph, an instrument that's able to measure this phenomenon. In the 90s, he spent his nights scrutinizing the movement of stars, searching for an exoplanet. But back then, his colleagues did not take him seriously.
So when I told people that I was beginning to develop a technique to discover planets around other stars, people were embarrassed, and they would look down at their shoes and they would say, "Oh, the weather's very nice today, isn't it?" And they were embarrassed for me. They were embarrassed for me because they knew that my career was over.
Jeffrey Marcy was not the only one to launch into this crazy race. In the middle of the 90s, on the other side of the Atlantic, in Geneva, Michel Mayor and one of his students back in the days, Didier Queloz, also had the same challenge, trying to find an exoplanet while studying the movement of stars.
It's very difficult to find a planet. Planets are very small objects that barely trouble their stars, so the technical difficulty is enormous. This was a field with no major results, where we were hoping to find the first planets, so it was really a classified field.
People saw planets around other stars on Star Trek and Star Wars, and they read about them in science fiction novels, but it was fiction. And everybody realized that there's a distinction between fiction and science.
In 1995, the Swiss moved into the observatory of the Haute-Provence in France. They also built a spectrograph with the teams of France's CNRS to measure the movement of the stars. When they started their observations, Michel Mayor and Didier Queloz were expecting a long and exhausting search. Their American rival had already devoted 13 years of his life to hunting these planets with no results.
I began searching for planets around other stars in 1983, and I worked every day, weekends. I worked at night until midnight every night, trying to develop the techniques, the optics, the software. But I didn't have any success.
On their side, the Swiss had also spent several years on the development of their spectrograph. But just a few weeks after beginning their observations, Didier Queloz could not believe the data coming from his instrument.
Surprise! One of the stars of the Pegasus constellation, 51 Pegasi, started to show some variability. It was completely unexpected and I would say almost dubious. So our first reaction was to think that there was a mistake somewhere.
There seemed to be a dancing star in the sky, which meant that there was a revolving object. It was so unbelievable that the Swiss kept their discovery a secret before redoing their measurements 6 months later.
So it was at that moment that Didier and I allowed ourselves some madness. We made a toast with some champagne and cake.
Some claret de Die.
Exactly, some claret de Die. Because at that moment we were like, yes, we're not missing something. It's a planet.
The star that they observed is located in the Pegasus constellation, over 50 light-years away from our solar system. Around that star, 51 Pegasi b, the planet that they discovered was nothing compared to the Earth. It looked like a giant ball of gas, which was very close to its sun, whose years could only last for 4 days.
It's easy to figure out. Imagine Jupiter, just a little smaller, because its mass is about half its size. And as it's so close to the star, 8 times the diameter of the star. Its temperature on the surface is absolutely immense. We're clear on this. There's no way that such a planet can have life, because that planet is giant, gaseous, and above that has some terrifying temperatures.
Such a planet would be so extraordinary that, according to the theories back in the days, it might not exist. It is much too close to its star. In our solar system, our planets are well in order. Within the proximity of the Sun, there are small rocky planets: Mercury, Venus, Earth, and Mars. Then, much further, there are giant gaseous planets: Jupiter, Saturn, Uranus, and Neptune. The planet which Michel Mayor and Didier Queloz found looked more like Jupiter. But the problem was that it shook up this establishment order. It was located right beside its star.
So that's why the discovery of 51 Peg b was so shocking. How could it be with our own solar system and a theory that makes perfect sense for Jupiter's far away, that 51 Peg as a Jupiter-sized planet would be found over here? It's crazy. It doesn't make any sense. It almost seems to defy the laws of physics, but it doesn't.
One of the major consequences of this discovery was that you needed to take into account a major physical ingredient, which was that planets form far away, then they migrate and get close to the stars. So that's how 51 Pegasus shook our knowledge about the formation of planets.
This was a revolution. The solar system was no longer the only model. Didier Queloz and Michel Mayor's discovery in 1995 was historic. It made news around the world. And today, it is the subject of a number of exhibitions in museums like this one in Geneva. This discovery launched astronomy into a new era, the search for exoplanets.
Here is an old friend.
Yes, it's a planet that disturbed our lives.
We didn't make the discovery in one day, but yes, absolutely. This planet is emblematic because it is the start of a long series of long discoveries of other exoplanets.
After the discovery of 51 Pegasi b at the end of the 90s, Michel Mayor, Didier Queloz, and Geoffrey Marcy detected other planets. but the quest became somewhat monotonous, with gaseous giants every time. The exoplanet researchers wanted to find other types of worlds, similar to Earth, for example. And at the time, not all scientists were convinced that this quest made any sense. The exoplanets that were detected remained invisible.
When the first planets were discovered around other stars, most people were not sure they were really planets. Maybe these planets that we thought we discovered didn't exist at all. Perhaps the stars were pulsating, giving us a changing Doppler effect. Or maybe the star had another star orbiting it in some crazy orbit, and it was just a star and a second star. So maybe the planets we were finding were not really planets at all.
How could they convince the scientific community that these planets existed? And how could they find planets where life could develop? In 1999, a young Canadian student, 25-year-old David Charbonneau, took an interest in an observation technique that revolutionized the search for exoplanets.
Our sun, and the sun has a planet. A transit is very simple. Every time the planet goes in front of the star, it blocks some of the light, and so for this brief period of time, we see the star get just a little bit fainter. The planet continues on its way, and the star gets brighter, and nothing happens until the planet makes it all the way around once again. The second time we see a transit, we've learned not only how big the planet is, but also how long it took to get around, and therefore how far away the planet and the star are.
David Charbonneau wanted to observe a transit, the decrease in luminosity of a star through the passage of a planet. And precisely, in 1999, Michel Mayor discovered a new exoplanet around a star by the dear name of HD 209458. According to his observations, the planet passed in front of the Sun every 3.5 days. So David Charbonneau decided to target this star with his telescope. He settled in Colorado. And with his small amateur telescope, started to study the tiny variations of light of the star for about 10 days.
The first time I saw this curve, of course, was on my computer in 1999 when I was plotting the data for HD 209458, and it was one of the most exciting things I'd ever seen, and I got to be the first person ever to see that. The star is constant in brightness, except for the first time the planet goes in front of the star. We can see by how deep the transit light curve is, how big the planet is, and then importantly, the second time it happens, it tells us what the orbital period and therefore the distance is between the planet and the star.
This simple curve brought new and crucial information on exoplanets. So far, the first method of detection, based on the movement of stars, only helped to estimate the mass of the planet. But now, it was also possible to measure its size. Sketches of the planets discovered could now be made and compared to the only object of the universe where life is detected, Earth. But what makes our Earth so welcoming? What are the vital elements of comfort on the planet that enable life to develop? The reason why it is better to live on Earth than a gaseous planet is, first and foremost, because it is solid and rocky. It is now possible to know if a planet located light years away from us has that level of comfort, thanks to the transit and movement of stars.
Once you see the planet go in front of the star, then you know the true mass of the planet, but also you can figure out its size. And if you know the size of a sphere and the mass of a sphere, you can calculate the density. And ultimately, what we hope to do is find planets that are the same size as the Earth, but also very, very dense and must be made of rock. Of course, if you're interested ultimately in looking for life in the universe, those are the planets you really have to find. And so it's really only with transits that you can actually get those critical measurements that tell you maybe we have an Earth-like planet.
But for life to develop, there must be more than just a rocky planet. There must also be mild temperatures to preserve a precious element, water in liquid form.
If you put a planet very close to its star, then obviously if there's any water on the planet, it'll boil and be in the atmosphere. It'll be a gas, so not a good place to call home. As you move the planet farther from the star, there'll come a point where all the water condenses and you have an ocean. That's the beginning of the habitable zone. Then if you keep moving the planet away from its star, you get to a point where it's so cold, you're not getting enough energy, that now the liquid freezes. So it's a solid, and that isn't a good place for life either. So there's that small range, not too hot, not too cold, and we call that range of distances around the star the habitable zone.
Soil and liquid water. But another element is also vital to have life. It's what protects us from sun rays and allows us to breathe, the atmosphere.
We got very excited because we realized once the planet went in front of the star, we could use the light of the star like a flashlight shining through the atmosphere of the planet.
And we can analyze that light. Now, the interesting thing is that when the light goes through the atmosphere of a planet, some of the light gets absorbed by the molecules that are in that atmosphere. And so you can learn whether there was water molecules, carbon dioxide, methane. So the atmosphere and any life on the surface are intimately connected with each other. By studying the atmosphere, we can learn a little bit about the life that might be on the surface.
The ideal exoplanet is then a twin of planet Earth. It must be rocky at a good distance from its star and have an atmosphere. But it is impossible to detect this type of planet from the surface of the Earth. These rocky planets are small in size. When they pass in front of their star, the decrease of light is minimal. And our atmosphere, just like a filter, blurs the light that comes from the stars, which prevents us from detecting these small variations.
Jupiter going in front of a sun-like star blocks about 1% of the light. But the Earth going in front of a sun-like star blocks less than 1 part in 10,000. So it's a tiny, tiny signal, and you really need to be above the Earth's atmosphere to hope to see it.
The atmosphere is a shield which prevents us from finding little planets like Earth. How can we know if these planets exist? And how can we observe them? At the end of the 90s, the hunters of exoplanets had one dream: to send a telescope to outer space to finally be able to find what they were looking for: inhabitable worlds. At NASA, an astronomer named Bill Barucki fought for decades to launch a telescope into space in order to search for exoplanets.
And then finally, I think in the year 2000, and shortly after the discovery of the transits of 209458, his proposal was accepted. He brought together a big team. He finally got the money. It was a very complicated spacecraft, and so it took 9 years to build, and it was finally launched in March of 2009.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, engine start.
After years of waiting, finally, on the 7th of March, 2009, a rocket called Delta II was launched from the base of Cape Canaveral in Florida. On board was Kepler, a space telescope and super hunter of exoplanets, which carried with it all the hopes of the astronomers.
Pressure's looking good.
It was absolutely spine-tingling. The rocket, went up 5, 4, 3, 2, 1, and it went up, and I couldn't believe that it just kept going and going and going and going until you couldn't see it anymore. I thought maybe it would blow up on the launch pad or that the rocket would go into the Atlantic Ocean, but none of that happened. It was perfect. So it was an amazing moment.
Mach 1, vehicles now going supersonic. Motor chamber pressure is beginning to trail off.
Kepler was the first time, it was the first time in human history that humans had built an instrument that would actually be able to find a planet just like the one we live on. And so with that launch and watching Kepler go up into the night sky and then following the orbit through space, I knew that for the first time we were on our way to potentially making those observations.
We see separation, and we have ignition of the air-lit solid motors.
If we could just discover a few planets the size of the Earth, that would give us some indication. We had no idea what would actually happen.
With Kepler, a new adventure began, in search of Earth-like exoplanets. The telescope was set to continuously film for the duration of 4 years about 150,000 stars and track minor decreases in luminosity caused by the passing of planets.
Kepler is essentially, it's a 1-meter telescope, so it's a big telescope, and it looks at one patch of the sky uninterrupted for 4 years. The light is recorded on essentially a large digital camera, similar to the ones that you might know from your telephone, but it's an enormous camera. The actual camera itself is about this big, the actual silicon. And then that camera has countless pixels which record the light from all those different stars. In fact, there's such a big camera, Kepler wasn't able to return all the data. It had to pick the stars that it wanted to study in advance, and it only returned the data from about 150,000 stars, chosen from more than 5 million that it could have looked at.
The data to analyze were immense. David Charbonneau and Geoffrey Marcy were part of NASA's team for the processing of Kepler's results. And after a few months, they eagerly discovered their first planets.
The first harvest of Kepler data was, we felt like children opening a treasure chest, because the instrument worked, and you could see small planets in very short orbits. Of course, those were the only ones we could find at the beginning. After only a few months of data, you'd only be able to see planets that were very, very close to their stars. For me, I think the first mind-boggling discovery was one star with different planets.
The astronomers marveled at these planets which, as in our solar system, danced around the same star. But Kepler had much more to reveal.
We were studying one star discovered by Kepler. We called it Kepler-10. It's just a star that dimmed, we thought, due to a planet, a small planet, very small planet. But we wondered whether this small planet was rocky or made of gas. And the density was amazing. We got about 8 grams per cubic centimeter. And of course, the Earth has a density of about 5.5 grams per cubic centimeter. So this was a planet even denser than our own planet Earth. And that proves that it must be made of rock.
The discovery of a rocky planet like the Earth was exceptional. But the comparison stops here. Kepler-10b was a world of lava where temperatures exceeded 1,500 degrees, which made it impossible to believe that life could develop in such a furnace. To find small planets with good temperatures in a habitable zone, patience was of the essence. These exoplanets were further away from their star. It would then take them several months and even years to completely revolve around their sun.
Since that time, Kepler has found planets that are even more Earth-like. And I would say, for me, one of the most exciting systems is Kepler-62. That has got 2 planets, maybe one that's at one edge of the habitable zone, one that's a little bit farther out. And they're only about 1.5 times the size of the Earth. So still bigger than the Earth, but probably rocky worlds, and maybe even worlds with oceans on them.
So Kepler accomplished its mission by discovering Earth-like planets. It is still impossible to know their atmosphere and to find out if life has developed on their surface. These planets are too small and too far away to make such analysis. But they could be perfect twins of our planet.
For these planets, we know their size, we know their temperature, but we don't know for sure whether they have oceans. So the exciting thing for me is to speculate, yes, maybe that planet really does have life on it. What's the next experiment to go and study those planets and actually find out, do they have oceans, and is there actually life? And if there is life, then in the future we might even imagine trying to investigate how similar or different the life is from life on the Earth.
Kepler's results were fascinating. Within 4 years of observation, it discovered over 1,000 proven planets and 3,000 awaiting confirmation. The telescope found habitable worlds by scrutinizing less than 1% of the sky.
And so we can do the statistics of these planets. We learn the following amazing fact. When you look up into the night sky, approximately 1 out of 5 of all of the stars has a planet the size of the Earth with a temperature nearly the same as that of the Earth. Earth-sized and nearly the same temperature as our Earth. 1 out of 5 stars have planets that remind us of home.
Kepler has disrupted our perception of the universe. There are probably billions of exoplanets in our galaxy. However, factually, the satellite only detects curves, signs of presence, and the planets remain invisible. Will it ever be possible to see these worlds, which are light years away from our planet? That is the feat of the astrophysicist Anne-Marie Lagrange. She was one of the first to achieve what seemed impossible: the image of an exoplanet.
Most of the methods that worked so far consisted in finding signs of the presence of planets around the stars. My objective is to see these planets, to register their light and analyze it.
Anne-Marie Lagrange has devoted her life to the observation of one star, Beta Pictoris, located 63 light-years away from our Sun. And in 2008, she produced this snapshot. At first sight, there is nothing exciting about it, but this image is exceptional. Above the star, there is a luminous tiny dot of a few pixels, an exoplanet.
I had to wait for 2008 to find that planet. It taunted us for 15 years. There are a few tiny shining pixels that you can see here. In fact, they are very important because they prove that we can detect planets through direct imaging.
Needless to say, these images are not yet spectacular, but it's a great achievement to discern exoplanets from the light of their star. But how did Anne-Marie Lagrange succeed in finding these worlds, which were once invisible? In order to understand, we must go to the other end of our planet, to the north of Chile. In the midst of the Atacama Desert, the area seems deprived of life. Hidden in this lunar setting is an underground base in which 100 astronomers are living. They come to this desert from all over the world to use the most powerful astronomic instruments of the planet. Above the base, on Cerro Paranal, at 2,635 meters in altitude, are 4 steel giants. 4 telescopes from the European Austral Observatory, which scrutinize the sky of the southern hemisphere. This is where Julien Girard, a colleague of Anne-Marie Lagrange, works.
We're here on the Paranal platform. It's one of the most favorable sites in the world for astronomic observation. As the crow flies, the Pacific Ocean is only 12 kilometers away. And there's what we call an inversion layer. The clouds are confined at the same altitude, well above the sea. So that's why we chose this site for observation. We're almost always above this sea of clouds, with a sky that is perfectly clear.
A supernatural scenery which offers over 350 nights a year without a cloud above the telescopes. The conditions are ideal to observe the sky and look for exoplanets. At sunset, another night of observation can begin. Slowly, the telescopes start to move. Hundreds of tons orientate themselves with much caution to avoid getting any dust on the heart of the system, a parabolic mirror of 8.2 meters, whose role is to capture the light of the stars, the precious photons which cross the universe to get to us. At the base of one of the telescopes, a black box stays on the lookout for the photons that come from the exoplanets. This instrument is used by Anne-Marie to produce images of the invisible worlds. What goes on inside the black box was prepared here in Grenoble.
The challenge of detecting planets comes with the control of the light that arrives and with the detection of small photons of light that come from the planets.
In this laboratory, everything happens just like inside the black box in Chile, except that here, the light of the stars is simulated with a laser beam. But how does this instrument which distinguishes planets from their suns really work?
Alexis is going to turn on a button that will allow us to hide this star with a focal mask.
The first step consists of removing the light of the star by turning it off with a mask.
There's a lot of light that comes from the stars. We don't have much light compared to what comes from the planets. We have to remove most of the light from the stars to be able to see the little signal that comes from the planets.
The light of the star disappears, but it is still confusing, since there is still not any planet.
As it now travels through the atmosphere, when we make observations with the telescopes on Earth, the luminous rays from the stars are diverted in all directions all the time. In just a few milliseconds, they take different trajectories. So after we make observations with our detectors, the images are not that clear or pronounced. Instead, there's a big mark with light spread all over.
To have a clearer view, the deformable mirror corrects the disturbances of the atmosphere and allows us to finally see a small light to the right of the star, a planet. This is how, from thousands of kilometers in Chile, the telescope captures the images of exoplanets. When the sky lights up, the telescope orientates themselves slowly towards the stars. On Cerro Paranal, everywhere is calm. No light, not even the slightest, disturbs the observations. The show of the Milky Way is enchanting, but the astronomers themselves are shut in the control room. From his computer, Julien Girard makes live observations of images produced by the instrument, which hides that light of the stars. He looks for signs of the presence of exoplanets. The star that he's studying tonight has not yet revealed all its secrets.
Our solar system is about 4.5 billion years old, and that really makes it a baby solar system. The circle that we see here is real. It's a sign of astrophysics. So here we have a protoplanetary disk, seen straight from the front since it is completely circular. So that right here is some dust around this young star. As for the disk, we suppose that it is made up of planets, or that the furrow inside it was done by a planet or by several planets.
For now, imaging only allows us to see planets that are giant and far enough from their star. But these hidden worlds are now revealing themselves to us.
Seeing direct photons from extrasolar planets and knowing that we are really not alone, even if they are gaseous planets for now, where nobody is living out there. But it's still quite impressive. Maybe there are other objects where life could be found. Even if we can't detect them, it's possible that we might one day. And it's truly motivating to start this quest.
With the observations that we've carried out so far, we've only touched the field of planets that are a little far from their star. But there's much to discover.
These images are becoming more and more precise, but we are far from the mark. The high-definition image of an exoplanet will not be done soon. So how would we know what happens on the surface of these worlds which are so far away? How can we portray their climate? This is the mission of Frank Celis. At the observatory in Bordeaux, this astrophysicist collects the data from the telescopes and simulates what happens on the surface of the exoplanets. Far from astronomic instruments, with his computer, he creates meteorological maps of these new worlds.
Any progress?
Yes, well, I've just received the last results of the simulation.
Today, with his colleague Jérémy Lecomte, he is focusing on a rocky planet in a habitable area. But on this one, the weather is quite different from our planet.
This planet, Kepler 186f, we think that even if we've not been able to observe it, we're convinced that it shows only one side to its star, the same way the Moon always shows one side to the Earth. And that has climatic consequences that are quite dramatic, because a whole hemisphere of the planet never gets sunlight.
So here, for example, on this side, we mainly see humidity that is stronger on the day side. In fact, it's just like in the tropics. The sun evaporates a lot of water. And thanks to atmospheric waves, the winds carry this humidity to the night side, where there will be water in the form of rain or in the form of snow.
The worlds that Frank is studying are so surprising that they sometimes go beyond the craziest stories of science fiction.
The writers and authors of science fiction, they don't have the same constraints as scientists. So they really did some exploration, whether in filmmaking or in books. And they sometimes imagined and described configurations that we actually find.
In Frank's library, there are hidden worlds of science fiction which are very real today. As in this 1953 story, in which the author imagines an explorer landing on Mesklin, a planet with very strong gravity.
Lackland has a mass of about 80 kilos. His spacesuit, which is a technological miracle of its kind, weighs as much. So on Mesklin's equator, both men and spacesuit weighed approximately 425 kilos. He would never have been able to take one step without a cutting-edge device on his legs. So what's so fascinating is that we don't exactly have Mesklin in the inventory of exoplanets. But we have planets with a weaker gravity than Earth, then planets with much stronger gravities. For example, one extreme case is the planet that's called Kepler 10c. It's a planet that's about 2.3 times the radius of the Earth and weighs 17 times more. So on this planet, we have a gravity that's about 3 times the Earth's gravity, which means that a person who weighs 80 kilos on Earth will weigh about 240 kilos on that planet.
Science fiction authors have also described ocean planets entirely covered with water.
There's an exoplanet called Gliese 1214b that was discovered by David Charbonneau during his project M-Earth, which has a mass and a radius that make us think that we have here an ocean planet, probably without any continents and very rich in water. So can life find its way in a world like this? That's a question that we're asking ourselves.
NASA has discovered another planet, a dream for all Star Wars saga fans. Kepler 16b revolves around two stars. Just like Tatooine, the planet where Luke Skywalker enjoyed his double sunset.
For me, it's a dream come true. We've come full circle. Because I saw Star Wars in '78, when it was released. I was 6 years old and it blew up in my face, so to speak. I saw the opening sequence where they show that planet. I grew up in it and was fully immersed. So to see that the work I'm doing today is a match to these imaginary worlds, that reality is catching up with fiction, and that we're just at the start of this exploration, for me, it's just amazing and fantastic.
Science fiction surpasses reality again on one point. Extraterrestrial life has yet to be detected in the universe. And even if we find an exoplanet, that is the twin of Earth, rocky with water and a welcoming atmosphere. Would it be sufficient to say that there is life on the surface? Is life a common phenomena that can develop itself everywhere in the universe? Or is it an exceptional event that happened only one time on Earth? To answer this question, we must first understand how life initially appeared on our planet. That is a mystery that astrobiologist Louis Le Sergent d'Ondecourt is trying to solve in his laboratory of Orsay on the outskirts of Paris in order to reproduce the event that enabled life from inertness on our planet.
The Earth was formed about 4.5 billion years ago, and life appeared here about 3.8 billion years ago. What is really interesting for me in the laboratory is to see the real chemical conditions that prevailed with the appearance of life, so what we could describe as the emergence of life.
The basic elements of life are present everywhere in the universe. But to know if life can appear elsewhere on exoplanets, we must first understand how the pieces of the puzzle fit on Earth to create the living.
All the elements that you have here actually come from stars. So the link between the cosmos and the fact that there's inertness and life is quite obvious. But for me, the problem is that with these puzzle pieces, I have no idea how to link them together. And then, as I'm the one who's doing it, in a way it's like I'm cheating. So I have to get around the problem by asking, how am I going to organize the matter by intervening on it as little as possible, but in conditions that, in some way, duplicate what happened on Earth at that time.
In his laboratory, among all these pipes, Louis d'Ondecourt is trying to reproduce the birth of life. He plays with the molecules that are present in the universe, like methanol, ammonia, and water, then sets them in conditions that existed on Earth several billion years ago. And he observes what happens. For now, he has succeeded in creating elementary bricks of life, like amino acid and sugar. We are far away from living cells. But for this astrobiologist, solving the mystery of the appearance of life is essential to determine on which exoplanets this phenomena could appear.
If we get results that can prove that there are chemical systems that are well selected and suddenly take the place of all the others, then I think that at that moment we would quickly have the tendency to say, even with only a telescope, that such a planet is not interesting, but that one, yes, it has an interest. And I think that for exoplanet researchers, that would be an extremely important motivation.
The scientific quest for extraterrestrial life is on, thanks to the research of astrobiologists and the discovery of exoplanet hunters. We may one day detect other worlds as fertile as the Earth. New instruments will soon allow us to better observe exoplanets. In 2018, the James Webb Telescope will go out into space. And on Earth, in 2024, a giant telescope of 38 meters in diameter, the extremely large telescope in Chile, will help to produce more precise images of these worlds. The field of exploration is incredible. 2,000 exoplanets have been detected up to now, but there are billions more to discover. This adventure, which was launched by a few astronomers in 1995, has only just begun and is set to be one of the most passionate that science will ever know.
It's wonderful to look back over the last 20 years and realize that at that time we had no planets at all around other stars. We weren't sure whether our solar system was rare or common. Now we know that Earth-like planets probably are common. And I feel lucky and somewhat proud that I and Michel Mayor and David Charbonneau, a few other people, made major contributions to this baby field, still growing.
For me, the big excitement is I would like to start my career as an astronomer and before I retire, end up as a biologist. This is the first generation where we have the technological ability to go and look for life in the universe.
People have been asking themselves these questions for over 2,000 years and have debated about it for the past 2 millennia, mainly on a philosophical level. It's an enormous privilege in our era to be able to transform this old dream of humanity into a subject of current science.
Thanks to these men and women who have discovered new worlds several light years away from Earth, we will never look at the sky in the same way again. Above our heads, behind a star, probably hides a planet that will profoundly change humanity's destiny.